Good afternoon, everyone. We live in a world which is data centric. And as a result of this, our industry, the information technology industry, is in rapid transition. I have had the privilege of working in computing and communications now for about 40 years. I'm a little bit older than I look, I've been told. I actually programmed mainframes a long time ago in undergraduate. Used mini computers, of course, in college, and PCs. And then at Sun Microsystems, I had the privilege of designing Sun's first multi-microprocessors, which actually kind of changed that industry. And then had, again, the privilege of watching the internet grow by founding Juniper, which a company that I still work at. But from this perspective, I can tell you that there is something very big about to happen in the world of information technology, and in particular, the way in which data centers are built and they are deployed. That is about to change in a very big way. Now, why is that? We can actually, whenever we want to understand something, it's important to look at what are the fundamental forces that move the world. I've had a long time to think about this, and my analysis is that there are 5 key trends that are in operation today. You can call them forces or trends that will affect how information technology is built, how it's used, and how it's deployed. I'm a technologist at heart, and so the things that I think about mostly are technology and where technology is going. And these 5 trends are: we're living in a hyperconnected world. There's a data explosion that many people have spoken about, Young has spoken about. AI and machine learning is a very important force. Something that nobody's spoken about is end of Moore's law, and then finally the implications of living in an insecure world. Let me talk about each of these in turn. We live today in a hyperconnected world. If you had asked 25 years ago that the world would be connected together the way it is today with the internet protocol, people would have laughed at you. They actually did laugh at me when I was looking for money for Juniper. They actually did laugh. And today, we can look back and see that the internet has revolutionized all communications. It is the foundation for today's infrastructure, but it also lays the groundwork for tomorrow's infrastructure. And the main implication of living in a hyper-connected world is that every application that I can think of that human beings find useful or that machines find useful is also a communications application at the same time. So this is sort of the essence of living in a hyper-connected world. All applications are communications applications. And as a result, we should reflect that the engines that we build for data centers also have to pay attention to this ratio of communications to compute actually going up very dramatically in the last 20 to 30 years. So that's the main implication of this trend. The next trend is a data explosion. And you can almost think of this as being a gold rush for collecting data. Now, why is this? Well, it turns out that when human beings want to have insights, and insights are some of the most important things that we do have, we are able to have insights from relatively small samples of data. But when we're confronted with very large amounts of data, we are at sea. It turns out that machines, when programmed with very simple algorithms, can actually provide us extremely powerful insights on top of very large amounts of data. And This realization is actually called big data. And this realization people had about probably 15 years ago now. And as a result of that, everybody wants to collect data. Google wants to collect data, Facebook wants to collect data, Amazon wants to collect data. And the reason they're collecting data is not just to have insights. Those insights can be used to make money. So the connection between large amounts of data, machinery to operate on this data, and then finally insights, and then insights into money, that's the chain, the value chain that you need to remember. It's very, very important. Now, what's the implication of this data explosion on computing or computing infrastructure? It's very simple. The amount of data that we need to process cannot anymore be stored on a single server. It has to be sharded across hundreds and even thousands of servers. The moment you do that and you try to compute on that data, the ratio of communications to computing, again, shoots up dramatically. With the revolution of solid-state storage, particularly pushed by Samsung, has led to a 100-fold increase in the performance of solid-state storage compared to rotating media. That, of course, pushes on the networking infrastructure inside data centers in a very, very dramatic way. So that's the main implication. The main implication is that the ratio of communications to compute has gone up yet more. Well, AI/machine learning, it's really the next step in automation. Probably the single biggest idea of the 20th century was the idea that John von Neumann had of the stored program computer and the notion of being able to program machines as opposed to wiring them up to do computation. Well, it turns out that inspired by the human brain, we can build machinery that we don't have to explicitly program anymore. And while AI is not a new idea, when I was at Carnegie Mellon as a grad student, I actually went there to study AI. But the promises that AI made were not fulfilled for a long time. But I think this time around, we are really on to something. And what will happen is that the amount of data that AI needs to function is actually very, very large. So in a sense, there's a heavy overlap between artificial intelligence, machine learning, deep learning, and the notion of big data. You can almost think of AI or deep learning and machine learning as a way to utilize very, very large amounts of data, derive insights from this data without having to explicitly write programs. I almost dare to say that perhaps in 20, 30 years, this idea that we would be sitting in front of keyboards and writing programs may be over. I don't know this for sure, but this might happen. So if you're thinking of sending your kids to Code Academy, etc., this might be a little bit old-fashioned in a decade. But I'm not sure about this. And so you can see AI actually as a subset of big data, but eventually, perhaps it'll go to encompassing all of big data. This may happen. The next trend is something that has been missed by our industry, and it's shocking to me that we have missed it. It's the coming end of Moore's Law. For the last 40 years at least, and actually long before that, the actual horsepower, the power delivered by, in terms of numbers of instructions per second, by computing equipment was doubling roughly every 18 months. And the observation that Gordon Moore made in the 60s was that the number of transistors on a chip was doubling every 18 months to 2 years. And some people have labeled Moore's Law as the performance was doubling. That's not what Gordon Moore said. He simply said the number of transistors is doubling. Well, it turns out that the performance of a silicon device is proportional to the number of transistors in that device multiplied by the clock rate of that device. That's the best case. You won't get any more performance than that. Well, both those numbers, the product of the number of transistors multiplied by the clock rate, is saturating. The workhorse technology of the last 45 years is something called CMOS. And we are, with 5 nanometers, approaching the end of CMOS as far as we know the laws of physics today. Now, human beings are incredibly innovative. Something new will come along, I know, but please don't hold your breath for this. The fact that the engines and the workhorse technology is plateauing should ask us to think, what next? Is it the case that the amount of performance that people need and the cost performance, people don't need any more performance? Are people going to be happy with just the level of performance that we have? The answer is a vehemently no. So it's our responsibility as technologists to ask the question, given this flattening of the Moore's law curve, for compute, for networking, for storage, what next? And I will tell you that I've thought most seriously about this problem. And I cannot see but two things. Number one is, we live in a distributed world, so the number of data centers has got to increase. Because today's massively scalable data centers, I can't supply any more power to them. So one obvious thing to do is to build more data centers with more devices. This one is obvious, and it's going to happen. But the second thing you can do, and this one people haven't actually latched onto yet, is that there was this golden era of computing. From all the way from 1945 or 47, when the notion of stored program computer was invented, to about 1990, to about 2002, when the performance was doubling. During this golden era, what happened was that all computing consolidated to a single architecture. That single architecture was the Intel instruction set and the general purpose microprocessor, and then a standard server with 2 x86 sockets. That has become the fundamental building block of data centers. Well, it turns out that if I take particular domains, take a domain like machine learning. If I use a floating point intensive machine, I can get about 10 to 20 times better performance than a general purpose CPU. So what you're going to see in the next decade is you're going to see a flowering of silicon architectures where I am building engines which are specialized to particular domains. We're already seeing this happen with the utilization of GPUs for machine learning. GPUs were designed for graphics, of course, but they do vector processing and matrix processing very, very well and efficiently with floating point numbers. And now people are specializing, building even more specialized engines where, for machine learning, we don't need high precision floating points. So what people are doing is they're building specialized machines for this. Well, one specialized machine that we at Fungible are building is a machine we call a DPU, or a data processing unit, to move data very rapidly and to actually connect different kinds of application engines to each other in the data center. So this specialization of silicon engines and the distribution of data centers to the edge are the two solutions that you should see happening very, very rapidly over the next 3 to 5 years. Now, the last trend is cybersecurity, or the lack thereof. Centralized data centers have huge targets painted on them. Not a single week goes by without yet another hack or some attack happening, data getting stolen or destroyed. And the problem with this is that many of these threats happen because the operating systems on which we build our entire application set have hundreds of millions of lines of code and hundreds of thousands of bugs. And it is not possible We don't know how to write perfect code. Nobody's discovered that. By the way, if any of you know how to write perfect code, please come talk to me, and you have the next $100 billion company. So because we don't know how to write perfect code, vulnerabilities in these operating systems are exploited to steal data and to create havoc. I think that there is a better way to do that, to have perhaps smaller units that are focused just on security. So that's the last trend that is going to affect the architecture of data centers. Now, today's cloud architecture looks something like this. You have end users, you have the internet, and then you have massively scalable data centers. And you have a little bit of caching at the edge. Of course, that's there. That architecture, this use of centralized, very large-scale data centers will need to be augmented by what comes next. And what comes next is an architecture where you have these massively scalable data centers, but in addition, you have what I would call edge data centers that are sitting much, much closer to the user. Now, there are at least 3 reasons why you need to have these edge data centers. One of them is that when your data is sitting 1,000 kilometers away, you don't feel as comfortable. So security is one reason why you might want to localize data. Okay? Second reason is that if you have low latency applications, doing a round trip to a data center which is thousands of kilometers away doesn't work. In fact, things like gaming or things like very, very low latency interactions cannot happen except if you put computing equipment very close by. And of course, there's economics. Note that all data, or not all data, most data is actually generated in a distributed manner. And so if it's generated in a distributed manner, and if it's hundreds of terabytes of data, transporting this data to a central location actually costs a lot of money. In fact, the cost of transportation is proportional to bandwidth times distance. So for all these 3 reasons and several more, we see that you will start to have edge data centers. And eventually, the car itself will become a data center. This was also pointed out by Young earlier. So let's go through this animation of... so what's going to happen with these edge data centers is that not only will you have caching going on, but you will have filtering going on for data that is generated, and any local computation that you need to do will be, in fact, done locally. Now, if you look inside today's data centers, as I pointed out to you, these data centers are built using servers, and these servers are compute-centric. They come to us from the PC era. In fact, when I look and I open up a server, it reminds me of the PC that I bought back in 1987. Now, ask yourself the following question. The ratio of communications to compute, given all the trends that we have, given the security problems we talked about, probably 30x improvement in the ratio of communications to compute, yet the machine that we have in the middle of the data center, the fundamental building block, the server, has a CPU at its center. And this particular architecture with the CPU at the center was fine when I had half a dozen I/O devices, which are slow, much slower than the CPU. But it doesn't work in today's world, where the network is running at 25, 50, and 100 gigabits per second per server. And so you need a different architecture tuned to the world of data and data processing. Well, what does that architecture look like? That architecture has, we believe, a data processing unit at its center. This data processing unit does 2 very important things. Actually, 3 very important things. First of all, it allows many, many, many servers to be connected to each other at very low latency and low cost. Number 1. Number 2, It does the impedance matching between packets sitting in the network and data structures sitting inside these application engines, like the GPU, the CPU, the TPU. Okay? It also makes storage be a first-class network citizen. So these are the three functions that the DPU does. And you can also see the DPU, which is a fully programmable device, but it is optimized for one and only one task, which is to move data very rapidly and to convert the data between the formats that the data has inside memory to the formats that it has on the wire. And you can see that this capability is central. You cannot get away without it. So whether you have a small edge data center or you have a massively scalable data center, I predict that the DPU will become the center of the building block that we call a server. So now, what will the future look like? We're back to the beginning of asking the question that we're in transition, but what will the future look like? Well, we believe the future goes from centralized data centers today to what I call data-centric computing. And in data-centric computing, you will have these massively scalable data centers. You'll have the internet as it exists today, somewhat modified. You will have edge data centers, and you'll have other, perhaps mobile data centers, where the data is mostly processed where it is generated, because this is cheaper, it's faster, and it's more capable. So that's the world that I see coming towards us very, very fast. Thank you very much.